All right, I have been looking forward to recording this video all day, and here the moment has come. This is going to be a really good one because we get to solve equations, but it's with exponential and logarithmic functions, and things are just weird and wonderful in this chapter. Essential question is, how do I solve the functions when x is either in the exponent or when x is in the logarithm? So far we've only talked about situations like this, where we could kind of like think about the answer, but I'm going to show you how to actually figure out the answer legitimately right now, and it's going to get awesome. So we're going to use two different main techniques. There are some equations where it will benefit us to make both sides of the equation look the same, and I'll show you what I mean by that. There are some equations where I'm going to translate either into or out of a logarithm, and I'll show you what those look like. We're going to do two examples for each technique, so hopefully you can kind of learn to recognize when to use each one. Anyway, let's get started. Okay, this one. Take a look at what's going on. This side of the equation, x is in a logarithm. This side of the equation, x is in a logarithm also. Now this is confusing because I don't really know how to get x out of a logarithm, but notice I have the exact same thing on both sides, right? It's log base 5 of something equals log base 5 of something else. Both sides of the equation look the same. This is technique 1. Both sides of the equation look the same. So for this side to truly be equal to this side, isn't it true that this needs to be equal to this, right? Because whether or not this is a log base 5 or whatever else, the point is I do have this on this side and this side already, so I need the middles or the insides to be the same. So what I can do is I can basically just ignore the fact that there are logarithms there. The logarithms are already equal to each other. I just need to make sure the insides are equal to each other. So I'm going to ignore the logarithms entirely because they're already equal to each other. And now this is a super easy equation to solve. This is like equations that you had a lot in geometry. Looks like x equals 2. I should probably do it this way so you're not confused. X equals 2. Yay, I'm done. And that was actually really, really easy. The issue is, this is another chapter where we may have, yes, the dreaded extraneous solutions. So I need to double check. Just like with square roots, where I'm not allowed to have negatives, as it turns out, with logarithms, I'm also not allowed to have negatives. And I did explain this in a previous video, but think about it. What power of 5 gives me negative 25? Well, it's not negative 2, because that reciprocates. 5 to the negative 2 is 1 over 25. So what? Well, there's no way to get it. So I need to make sure that when I plug this back in, it doesn't give me a negative under the logarithm. But look, if I plug it back in on the left-hand side, 2 times 2 is 4, minus 7, that's log base 5 of negative 3. This is no good because I have a negative under the logarithm. So this answer is actually extraneous. But that was my only answer, which means I have a no solution. Very unusual to get a no solution, but this one is a no solution. Okay, next. This is a really weird one, and I maybe should have done an easier example first, so let me just do an easier example to the side. If I have 5 to the x equals 5 to the 3x minus 5, wouldn't you agree that much like this last one, both sides have 5 to the power of something? This part of the equation is already equal. So I don't really know how to get rid of that 5 to the power of, but what I can do is, since this is already equal, now I need to make sure these are equal. So I can set x equal to 3x minus 5 and solve just like what I did in this example with the logarithms. The issue is this. I do not have the same base in both places. In fact, these bases are very, very different. One is 10, and one is 1 over 100. So what I need to do is I need to make sure I can get the bases to be the same. How? Well, something I can't do is I can't just say, oh, hey, let's do 10 to the negative 2. I know that 10 to the negative 2 is 1 over 100. I'm not allowed to do that. I can't just introduce a negative 2 here out of nowhere. But what I can do is I can look at the other side and I can say to myself, oh, 1 over 100, actually 1 over 100 is 10 to the negative 2, right? That's the same thing. 10 to the negative 2 equals 1 over 100. Yeah, they're equivalent. So instead of writing 1 over 100, I'm going to write 10 to the negative 2. And let me just write everything else down first. Now what can I do? Well, I have a power to a power. These powers I know are going to multiply. So still not doing anything to the left-hand side. On the right-hand side, I'll have negative 12x plus 2. That negative 2 distributes through to both terms. Great. Now I have the exact same base. Since the bases are equal to each other, I just need to make sure the exponents are equal to each other. So I need to make sure that 3x minus 10 is equal to negative 12x plus 2. And again, this is super easy at this point. Add 12x, add 10. Looks like x is equal to 12 over 15, which reduces to 4 over 5. Pretty neat. There's nothing that can go wrong with exponents. Remember that I can plug anything into an exponent. The domain of an exponential function is all real numbers, so I know that this is not extraneous. Nice. Now we're going to get into using the other technique. There is no way I can make these two sides look like each other. Look, x is in the exponent here. I don't even have an exponent on this side. So unlike this problem where I had two exponents and this problem where I had two logarithms, I'm not going to be able to do that over here. So what I need to do is I need to translate. I need to get this to a point where I can translate this into a logarithm. First of all, what I need to do is I need to probably isolate the power. So let's quickly divide through by 4. E to the negative 2x equals, I think that's 4.25, 17 divided by 4. Now at this point, remember what the logarithmic translation is. You need to have this super memorized, and I'm not writing it right now, but log base b of x equals n translates to b to the x equals n. Likewise, just like I can go from here to here, I can also go backwards from here to here. There are cleaning ladies being super loud outside my room right now. I wonder if it's coming through in the video. Anyway, a joyous little occasion. They're all laughing and just saying things that I don't understand because I can't speak Darija. Anyway, I have this situation, right? This is the situation I have. So I need to translate it back to a logarithm. Well, let's look. The base becomes the base of my logarithm. So log base e. This number on the other side of the equation becomes the number inside my logarithm. So 4.25. And then the x, the exponent, becomes the thing on the other side of the equation. Now, I have this memorized. You need to have this memorized as well, where everything goes. And you might be saying to yourself, how does this help me? Well, remember, log base e, that's the same as ln, right? Can you use your calculator to do ln? Yeah, you definitely can. So I have my calculator out. I'm doing ln of 4.25, and I'm getting 1.45. We'll just round to 2 decimals for now. Now all I have to do is divide by negative 2. So it looks like x is equal to negative 0.72. We'll just round it to 2 decimal places. Notice what I did is I made the translation. I isolated. Now this is a translatable thing. I translated it into a logarithm that my calculator could do. Notice that when I translate, now instead of the x being in the exponent, which is confusing, x is over here by itself, which is a situation I really know how to deal with. So make the translation. All right, we have one problem left. This is going to be the most complicated problem. Take a look. Okay, we have two separate logarithms. Also, on the other side, we just have a number. So I can't use technique 1 because both sides don't really look the same. They're not of the same format. I have 2 logs over here and 1 over here. But also, technique 2 really relies on me just kind of having a translatable, looking thing. Something that fits nicely into this translation formula. And this is also not the case here because I have 2 separate logarithms. But oh wait, what did I just teach you in the 7.5 video? I taught you log laws. I know how to take these two logarithms and make them into one logarithm. How do I do it? Well, I see that they're adding. I see that they have the same bases. That means I can write this as one logarithm where the insides are multiplying. Whoa, that's so cool. It's a FOIL problem inside of a logarithm. This is really exciting me as a math major, and I hope it's exciting you as much as well. I FOILed quickly while I was gushing about how cool this problem is. I used FOIL to simplify. Now I have just one logarithm and a number on the other side. So believe it or not, I can actually make the translation. Let me just write it so that you see what's going on here. Look, I have this situation. This is going to translate to this situation. So the base of my exponent becomes the base of my logarithm becomes the base of my exponent. The number on the other side becomes the exponent, and the thing inside goes to the other side of the equation. Whoa, I made the translation, and now I have all of these x's outside of a logarithm. Now I have a simple quadratic, and I put simple in quotes because really it's not that simple. Let's simplify some things. I know that 5 squared is 25. And I know that since I have a quadratic, I need to get a 0. So let's subtract that 25 over. And 4 minus 25 is negative 19. The reason that this is simple in quotes is because, do I know how to factor this? No, definitely not. Luckily, you have memorized the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You've memorized this because you know the song, and I told you it would keep showing up. So let's plug in some things. B is 5. B squared, so 5 squared. A would be 1. C would be negative 19. And then I have a 1 on the bottom as well. I'm going to pause the video and calculate the two different answers, one taking into account the plus, one taking into account the minus. So give me a second to do that. There are the answers. Yeah, if you plug that quadratic formula into your calculator, you get this answer with the plus and this answer with the minus. I need to check for extraneous roots, and I think you notice if I plug the negative in, definitely going to get negatives inside the logarithm. And for a broader explanation, look back at a previous example. This is going to be extraneous because it will result in a negative inside the logarithm. So my only answer is this. Whew, that was exciting. A logarithm problem where I used log laws, then made a translation, and then ended up using the quadratic formula. It's Christmas time for mathematicians like me. Anyway, that's all I have time for today. Just a summary, there are two techniques. If the sides look similar, you make both sides of the equation look the same, and then just make equal the parts that aren't equal yet. That was like example 1 and 2. Or if you have an exponent on one side or a logarithm on one side, you may need to translate to get the logarithm like I did in examples 3 and 4. You need to have that logarithm translation memorized. It's very, very important. All right, cheers.